If you strip away, like, the microchips and the glowing screens and all the software running our 21st century, you'll actually find that our modern world is entirely powered by a piece of technology that was invented before the Roman Empire.
Right, the basic physical gear.
Yeah, exactly. I mean, whether you're driving down the highway or getting power from a massive wind turbine or just relying on products built on automated assembly lines, you are completely dependent on this mechanical concept that hasn't really fundamentally changed its geometry in thousands of years.
It's true. We are essentially resting, the absolute pinnacle of human engineering on the concept of interlocking teeth.
Right.
And, well, it is a brilliant, enduring piece of architecture, obviously, but we have really reached the upper limits of what a rigid toothed wheel can actually accomplish in extreme environments.
And that limitation is exactly what we are exploring today. So welcome to this deep dive.
Yeah.
Today we're looking at a truly fascinating piece of research that was just published in the May 14th, 2026 issue of Physical Review Letters.
Yes, it's an incredible paper.
It really is. A team of scientists at New York University's Applied Mathematics Laboratory has managed to completely reinvent the gear. And the goal of our deep dive today is to explore how these scientists are reinventing that gear by removing the teeth entirely and using fluid instead.
Which sounds impossible at first.
Right. But we're going to look at how they did it and why this could fundamentally change how machines are built from here on out. So, okay, let's unpack this. Before we can really understand the solution, we have to understand the problem with this millennia-old status quo.
Yeah, to truly grasp the magnitude of what this NYU team, and they were led by Professor Jun Zhang, what they've accomplished, we have to examine the inherent flaw in solid mechanics because the story of the gear is ultimately a story about the physics of rigid bodies in contact.
Right, let's trace that history back for just a second to understand the stakes here.
Yeah.
I mean, we have archaeological evidence of early gearing systems in ancient China.
Mm-hmm.
But the most famous early example is probably the Antikythera mechanism from ancient Greece, right?
Oh, absolutely. The Antikythera mechanism is just the perfect case study. It was discovered by sponge divers back in 1900 off the coast of a Greek island.
Wow, 1900.
Yeah, they literally pulled it from a shipwreck as this calcified lump of corroded bronze. And when researchers finally managed to X-ray it decades later, they found this staggering level of complexity inside.
Like, how complex are we talking?
Over 30 interlocking bronze gears used as an astronomical calculator. It could predict eclipses, track celestial bodies. I mean, it proved that human beings have been precision engineering rigid gears for over 2,000 years.
That is wild. But it also perfectly illustrates the tragic flaw of the technology, right? Because that mechanism sat at the bottom of the ocean and basically fused into a solid block of useless metal.
Exactly.
Because whether your teeth are carved from ancient wood or cast in bronze or, I don't know, 3D printed from high-tech modern polymers, they all suffer from this strict zero-tolerance policy for error.
Right, because traditional gears require absolute, perfect mathematical alignment. If the teeth on two interlocking wheels are off by even a fraction of a millimeter, the whole system rapidly deteriorates.
Because it's all friction.
Yes. The entire mechanism relies on physical friction to transfer power. You are literally just grinding one surface against another.
It's kind of like being in a really stubborn relationship, you know?
Oh, how so?
Well, like if two people aren't perfectly aligned, they just sort of grind each other down until something finally breaks. There's no flexibility. With rigid gears, if there's a sudden temperature spike that warps the metal or just, the slow degradation over time, the mechanism seizes up catastrophically.
That's a great analogy. And what's fascinating here is that these very limitations, that exact rigidity and jamming, is exactly what pushed researchers to imagine an entirely new contactless alternative.
Right, because since rigid physical contact is the root cause of the gear failing, the logical but honestly totally mind-bending next step is to just remove the physical contact entirely.
Exactly. So that brings us to Professor Zhang and his team at the NYU Applied Math Lab. They didn't just tweak the traditional gear. They essentially submerged the whole concept in liquid.
Okay, so paint a picture for us. What does this experiment actually look like?
So the physical setup is wonderfully stripped down. Picture a simple circular glass container. And inside this tank, they placed two completely smooth cylinders side by side.
Wait, smooth, so no teeth at all.
No teeth, no ridges, no interlocking parts whatsoever, just two smooth metal columns. And they filled that circular container with a very specific, carefully calibrated liquid.
What kind of liquid? Just
A
water.
mixture of water and glycerol.
Okay, glycerol.
Yeah, it's a thick, syrupy compound. You often find it in soaps and antifreeze. The team used it to precisely tune the viscosity or the thickness of the fluid bath.
So, okay, here's the immediate problem that comes to mind when you think about this setup. You've got two smooth, clear cylinders sitting in a bath of essentially watered-down clear syrup. If you spin one of the cylinders, the clear liquid just sort of churns around. Visually, I mean, it would just look like a glass of water being stirred. How on earth could the scientists actually see what was happening inside this fluid?
That is one of the classic hurdles of fluid dynamics. Measuring invisible fluid forces is notoriously difficult. But the NYU team solved this by seeding the water-glycerol mixture with microscopic, neutrally buoyant tracer bubbles.
Oh, wow. So they basically injected thousands of tiny suspended tracking dots into the syrup.
They did. And then they illuminated the tank with targeted lasers.
That sounds incredibly sci-fi.
It looks amazing in practice. Suddenly, that invisible, clear fluid becomes a highly visible, glowing map of kinetic energy. Every single vortex, every little current, and microscopic eddy is illuminated in real time.
So they can actually map the currents.
Exactly. The researchers could watch exactly how the fluid molecules were behaving. The setup features one active cylinder, which is driven by a motor, and a passive cylinder that just reacts solely to the fluid's movement.
Okay, so the active one is hooked up to a drive shaft, spinning at precise speeds, and the second one just spins freely based on whatever the fluid is doing to it.
Precisely. The fluid itself becomes the transmission medium, basically replacing the metal teeth of a traditional gear.
Okay, here's where it gets really interesting, because setting up this experiment leads directly to the most surprising discovery of the whole research paper.
It does. When they ran the motor, they discovered that this fluid transmission doesn't just passively transfer the motion. The liquid spontaneously organizes itself into two completely different types of machines depending on the conditions.
Right. Let's talk about the first behavior, the one they call gear mode.
So when the researchers placed the two cylinders very close together inside the container, leaving only a really narrow gap of fluid between them, the liquid perfectly mimicked the behavior of interlocking gear teeth.
Meaning, if the active cylinder turns clockwise, it forces the passive cylinder to turn in the opposite direction, counterclockwise.
Exactly. And the mechanics behind this counter-rotation rely heavily on the specific viscosity, that syrupiness, of the water-glycerol mix.
Because it's sticky, basically.
Yes, exactly. When the active cylinder spins, the fluid molecules immediately touching its surface stick to the metal. It's a principle in physics known as the no-slip condition.
The no-slip condition, got it.
So as the cylinder turns, it drags that layer of fluid with it, which in turn drags the next layer, and so on.
Okay, so in that super narrow gap between the two cylinders, all that dragged fluid is just being violently squeezed together.
Squeezed and subjected to intense, localized shear forces. The fluid is essentially acting as a microscopic wedge.
Oh, I see.
The active cylinder pulls the thick fluid into the gap, and because there's so little space, that moving fluid exerts a massive frictional drag on the surface of the adjacent passive cylinder.
And that pushes the surface of the passive cylinder backward.
Right, resulting in a perfect reversed rotation, just like a standard gear.
Okay, that makes sense. But then we have the second behavior, the belt mode.
Yes. So the researchers took the exact same two cylinders submerged in the exact same liquid, but they moved them further apart.
And they sped it up.
They did. They significantly increased the rotational speed of that active motorized cylinder, and suddenly the fluid completely changed its physical behavior.
Okay.
Instead of acting like a gear and pushing the passive cylinder in the opposite direction, the liquid actually began to wrap around the entire system. It acted exactly like a mechanical conveyor belt, forcing the passive cylinder to turn in the same direction as the active one.
Wait, hang on. I have to push back on this a little bit.
Sure.
Because in the physical world, a solid gear cannot just magically transform into a conveyor belt. Like, I have a hard time visualizing this.
Yeah.
Can you clarify how the fluid is achieving this impossible double duty just by changing the distance and the speed?
It is counterintuitive, I know. This raises an important question about the unique properties of fluid dynamics. It's all about adjusting the viscosity and density of the mix, which allows the fluid to dictate the transfer of kinetic energy in ways that solid mechanics simply cannot.
Right.
By moving the cylinders apart and increasing the speed, the researchers changed the dominant physical forces at play. They essentially overpowered the localized shear forces that's squeezing in the gap and introduced macroscopic momentum and fluid inertia.
So basically, when the active cylinder spins fast enough, it isn't just dragging a tiny wedge of liquid into a gap anymore.
Exactly. It's accelerating a massive boundary layer of liquid. And because of fluid inertia, that fast-moving liquid wants to keep traveling in a straight line.
Like when you take a sharp turn in a car and you get pushed against the door.
Perfectly said. It gets flung outward away from the spinning cylinder, driven by centrifugal force until it hits the outer wall of the circular container.
And since it's a circular container, the wall forces the fluid to curve, right? Which creates this high-speed, sweeping river of syrup that travels along the entire inner perimeter of the tank.
Yes, and this sweeping perimeter current becomes so powerful that it completely overwhelms any localized friction between the cylinders. It literally acts as a liquid conveyor belt, sweeping up the passive cylinder in its wake and dragging it along in the same direction.
That is just wild. The fluid dynamically rewrites its own mechanical geometry based purely on the speed of the energy passing through it.
It acts as a shape-shifting machine.
Okay, so what does this all mean for you and me? Like, if we bring this back to practical applications, how does this actually improve the machines around us?
Well, co-author Leif Ristroff had some brilliant insights on this. Unlike traditional gears that require pristine, sterile conditions to function, these fluid gears are practically invincible to environmental hazards.
Right, because if you get dust or poor alignment in a normal gear, it jams.
Exactly. A steel gear might be highly efficient on a climate-controlled factory floor, but if you put that same steel gear inside, say, a micro-robot swimming through the human bloodstream, or an autonomous rover exploring a deep-sea thermal vent.
It's game over if something gets in the teeth.
Right. The moment a foreign particle enters, efficiency drops to zero because the machine breaks. But with fluid gears, if sand gets into the gap between these smooth cylinders, the fluid just suspends the sand grain, washes it around the smooth metal, and the cylinder keeps spinning.
Because there's no pinch point to jam.
Precisely. You trade a tiny percentage of raw efficiency for mechanical immortality.
Wow. And the other mind-blowing practical application from the Paker is the real-time adaptability, the ability to change speed and the actual direction of rotation in real time.
Yes, this is huge for industrial machinery.
Right, because in a traditional setup like a printing press or a factory robot, if you need the machine to suddenly reverse direction, you need a highly complex mechanical gearbox. You have to physically disengage the clutches, move metal teeth out of the way, and engage reverse gears.
Which requires a bulky, heavy, and fragile architecture. And it causes massive wear and tear every single time you engage a clutch.
But with a fluid transmission system, you can just eliminate the gearbox entirely. You don't have to rebuild the machine or swap out parts. You literally just turn a dial to increase the speed of the motor.
Exactly. If we connect this to the bigger picture, by simply crossing a specific speed threshold, you trigger the fluid inertia to overwhelm the shear forces. The liquid instantly shifts from gear mode to belt mode, and the passive cylinder seamlessly reverses its rotation.
You are changing the fundamental operation of the machine without moving a single internal component.
It opens up entirely unprecedented design possibilities for engineering. We are moving away from fragile, rigid systems and stepping into the realm of highly adaptable, fluid ones.
It's honestly incredible. We've taken quite a journey on this deep dive today. We went from the rigid, calcified wooden gears of ancient China to the frictionless, adaptable fluid gears coming out of NYU.
It is a massive leap forward.
It really is. And I know you had a final thought you wanted to leave everyone with regarding these design possibilities.
Yeah, I do. It builds directly on that idea of unprecedented design. I want you to imagine the future of robotics or autonomous vehicles. If machines no longer rely on rigid, perfectly aligned parts to transfer power, what happens when we start building machines whose internal components don't even have fixed positions?
Wait, like parts just floating around?
Basically, yes. If a machine can completely reorganize its own internal gears on the fly simply by changing the speed of a fluid, the very definition of a machine shifts. It changes from something rigid and mechanical to something fluid, adaptable, and almost organic.
Wow. Machines that operate more like self-organizing living cells than traditional engines.
Exactly. It completely changes how we think about engineering.
Well, that is definitely something to mull over. As you go about your day, take a look at the technology around you, whether it's the cars driving by, the mechanized doors of a grocery store, or just the ticking hands of a watch. Underneath it all, those ancient, rigid teeth are still grinding away. But maybe their 2,000-year reign is finally coming to an end. Thank you so much for joining us on this deep dive. Keep questioning the everyday objects around you, and we'll catch you next time.